In thermoelasticity, we study the response of a solid to changes of temperature and changes of stress, and how that solid deforms as a response of those. There are several applications in the subsurface, most notably and most intuitively geothermal energy. Geothermal energy can be shallow and deep. Generally, with shallow geothermal energy, we refer to applications which are mostly limited to a few tens of meters and have applications that are mostly for a residential home. However, when we go deeper and at a larger scale, we can go into other applications that involve higher temperatures and higher depths. As we're going to see in shallow geothermal energy, there is a, an impact of thermal stresses which is not very strong because the stiffness at shallow depths is not that high. But we're going to see that later at deep conditions, we have higher thermal stresses combined due to a change of temperature and also proportional to the stiffness of the material. And we're going to see also that in deep geothermal energy, we face challenges, for example, of creation of hydraulic fractures, of changes of the state of stress that can make vary the shear stresses and normal effective stress on fractures, and also that we might have significant changes of effective stresses caused to temperature. Recently, I put a presentation together where I discussed what were the challenges of geothermal energy. And let me share that slide with you over here. And this applies specifically to deep geothermal energy. And the questions are like the ones that you see over here, and this is an example which is happening right now in the state of Utah in the United States, called Utah Forge. And there are basically three challenges in deep geothermal energy, and also three completion types. One in which you inject a fluid through a mostly igneous rock, taking advantage of natural fractures. Another one in which you can facilitate the connection between wellbores through the creation of a hydraulic fracture. This is what is called enhanced geothermal systems. And also, there is a thermodality in which you can use a wellbore that just extracts heat from the rock without creating any fractures. So those three are linked to deep geothermal energy and are an obvious application of what we're going to see in a minute. But also there are some other applications of geothermal energy, like for example during drilling. During drilling, most times the temperature of the drilling mud is not the exact temperature of the formation. And usually, actually, the temperature of the drilling mud is lower than the temperature of the formation. And as a result, you can expect to have changes of stresses that occur around the wellbore and that favor a decrease of the hoop stress around the wellbore. And this reduction of hoop stresses sometimes can cause even tensile fractures and also lower the fracture gradient in wellbores. And this is just due to temperature. We also have applications of subsurface fluid injection and disposal. For example, just for fluid injection, we have applications of enhanced oil recovery, where you can inject water, carbon dioxide, other chemicals like polymers or surfactants. But many times the temperature of the injected fluid is going to be different than the temperature of the formation. Sometimes, as we saw in the previous case with the drilling mud, it could be lower. The temperature of the injected fluid is going to be lower, and this happens, for example, in water flooding. But there are some other cases in which, in order to reduce the viscosity of oil, you could inject water at a very high temperature, even in the vapor phase. This is what is done in some heavy oils in order to reduce the viscosity of the oil. So in both cases, either higher temperature or lower temperature, we're going to have to take into account these changes of stresses due to the temperature component. And also we have applications of gas disposal, and these are linked, for example, to the disposal of produced water and hydraulic fracturing water. And also, let me complete this. And also the injection of some other fluids like carbon dioxide for environmental purposes. Again, in these processes, you're going to have, if the temperature of the injectant is different than the temperature of formation, you may expect changes of stresses and strains due to this temperature coupling. Last example is also hydraulic fracturing. And hydraulic fracturing can also take advantage or could be affected by the temperature of the injected fluid. You could, for example, inject a very cold fluid in order to facilitate fracturing. This is what is called cryogenic fracturing. And the objective is to create a reduction of stress, local reduction of stress, that makes the process of fracturing easier. And it's similar to what we said before for drilling, in which the reduction of hoop stresses would make the tensile fractures to happen. With injection of a vertical fluid, you can also cause a local shrinkage of the rock that results in cryogenic fracturing. And I have an example about that over here. Let me bring the web browser into here. This is my friend Minsu over there doing an experiment of cryogenic fracturing, in which you inject liquid nitrogen into a rock and you produce a fracture just due to the thermal shock. And let me share with you also one of Minsu's photos over here. That this is an example of hydraulic fractures created in acrylic just by injecting liquid nitrogen. And I'll try to get these videos. If I can get these videos from Minsu, I'll share this with you. But basically, when you start injecting liquid nitrogen, even though if you're not above the fracturing pressure that you would need without a temperature shock, you will start creating fractures due to the local shrinkage of the solid. Okay, but also you may think about injecting a hot fluid for hydraulic fracturing. And in this case, what would happen is that you could heat up a formation, and by heating up the formation, you could cause an expansion of the fluids within the formation that would cause the matrix to expand and eventually to fracture. Let me show this here with an schematic. Let me get a little bit more of a space over here to draw. And okay, so let's imagine that we have a porous medium. And in this porous medium, we have fluids that may be subjected to a temperature increase. There is actually one study that shows that by heating up a rock with microwaves, you could cause some of these fluids to expand and sometimes even to change phase, go from liquid to vapor, and as a result of that, produce a cracking of the pores so that the entire rock fractures. And eventually, if you had, for example, let me add one more pore over here. If you had a connected fracture, you may split your sample into and cause this to fracture because of the heating of the pore fluid. In this case, this would be assuming that we have an undrained response within the pore space. And let me show an example about that. I have here now a video that shows that phenomenon. Okay, let's go slowly through this video. Let me here go full screen, and what we are looking at, it's someone on a camping day cooking on a rock slab, and you see the fire over there, right? And well, this person is comfortably cooking, but at some point the rock explodes. So what's going on here? It's exactly what we mentioned before. Is that let's come back. At some point, this rock might have been saturated. Probably they picked it up from a river nearby, and if it is fully saturated when heated up, and if the rock has permeability which is low enough so it doesn't let the pore pressure to dissipate, eventually it's going to fracture. And that's what you see here. It's actually a quite fast fracturing process. Once those cracks align, then you cannot stop it. It just fractures. And also because the steam is very compressible, it's a vapor, it causes this fracture to pop up so quickly and also to blow up. Okay, so you may wonder, could we use this for hydraulic fracturing? And I'm not quite sure about the answer for that, because the thought experiment that we're doing here is under unconstrained conditions, while in the subsurface, as you know, usually we assume that we are under constant vertical stress and under constrained conditions laterally because you have more rock around. So how would this phenomenon apply to this condition? Well, the theory of thermo-elasticity is going to help us answer that question. All right, so let's then dive into the theory, and in order to do that, let me motivate the discussion with just a very basic discussion here. And also we're going to agree on our convention of signs. All right, so if you were to heat up a solid, the change of temperature will be larger than zero, right? So what you would expect is that this would cause a solid to expand. For now, we're going to just talk about solids and not porous solids. We'll make the extension to thermo-elasticity later on. And in this case, the volumetric strain is going to be less than zero. So this is the convention that we're going to use. It's going to be also the general mechanics convention. And this is this is going to be, a dilation is going to be negative, and this is going to be the geomechanics convention, right? So this is going to be a process of dilation. If we have a drop of temperature, in which temperature decreases, then what we would expect is that the solid is going to shrink with time. And we're going to say that that produces a contraction or a positive volumetric strain. And also, we're going to assume in our equations that no matter what is the change of temperature, we do not have any shear strains. And this could be, I hope it is evident to see, but in an isotropic solid, changes of temperature are not going to cause any shear. You wouldn't expect these angles of this rectangular block to change because of a homogeneous change of temperature in a homogeneous solid. So let me add that this is what we have in an isotropic and homogeneous solid. This is going to be different, for example, in the case that we had an heterogeneous solid, like for example, some of our rocks are usually laminated and have a heterogeneity which is distributed in layers. So in this example, if I were to have a dilation coefficient which is different in this rock and in this rock, let's imagine that the first rock, it doesn't dilate that much as the other, you could expect a different dilation in these rocks and in this composite heterogeneous rock that would cause shear strains and stresses inside the solid. So for example, if this one is enlarging or getting longer in this plane, then let me see if this is going to work. I think this is good enough. You're going to create a shear on the interface that is going to happen because now you have a heterogeneous solid. Okay, so let me just complete this drawing by stating these are layers with different thermal dilation coefficient. And this is this is a parameter we're going to explain in a minute. Okay, so now with that convention, we're ready to get started in writing the equations of thermoelasticity. First of all, what we have to do is to expand our constitutive equation that relates stresses and strains. Sigma, the stress tensor, as we know, is proportional to strains through the stiffness matrix, and we're going to add now the term for temperature. So we're going to say that stresses also depend on temperature through this additional term that I'm going to explain in a minute what it is. And here we have the identity matrix, and remember that this is just for a solid. All right, so you already know this part. Let's explain the second part. This is what we're going to call the linear thermal dilation coefficient, beta. What we have over here is something that we already know, is the bulk modulus. Here we have the change of temperature. And delta T is equal to the temperature at a given time minus the initial temperature. And sometimes also we're going to refer to this variable delta T simply as theta, because we're going to use some derivatives and we don't want this delta to be there to avoid confusion. And last, you know this guy, this one is the identity matrix. Okay, so we're going to make a reverse proof of this equation. I could have developed this equation from incorporating the response of a thermoelastic solid into the equation, or I'm going to do the opposite, which I find it a little bit easier to explain, is to give the equation and to show that that's true. And this is what we're going to do right now. All right, so the first thing that we're going to do is to write the equation and to do an experiment, a thought experiment of, let me get more space over here, to do an experiment of unconstrained dilation. All right, so I have my equation in there, and here I'm going to do an experiment of dilation. In this experiment of dilation, I'm going to have a sample or a solid in 3 dimensions. Here I'm just making a 3-dimensional schematic, which is what we called unconstrained, or you could also say, in simpler terms, this is a free dilation. And what we're going to do is we're going to apply a change of temperature that is going to make this solid change size. Let's see what our predictions here on top predict for this type of experiment. Okay, so let me just, instead of writing everything again, let me copy this and paste it over here. And it is the same equation that I had before. We're going to apply the conditions to this equation to see how we solve it. Okay, since this is an unconstrained experiment, then that basically means that the stresses on the solid are going to be equal to 0. And therefore, if this one is equal to 0, then that means that any strain that it's caused by temperature is going to be a function of these material properties together with the stiffness. So what I can do is I can solve for the strains, and the strain tensor is going to be equal, moving this one to the other side, and then multiplying the inverse of the stiffness matrix, which is the compliant matrix, is just going to be this. Delta T, and let's use theta here, times the identity matrix. And let's go ahead and solve that. As we said before, we're not going to have any shear strains, so I'm just going to ignore the part of the shear strains, and I'm just going to write the volumetric strains epsilon 1, epsilon 2, 2, and epsilon 3, 3. So now this tensor, the first three components, which are these ones, and again, I'm not writing epsilon 1, 2, epsilon 1, 3, and epsilon 2, 3 because I know those are going to be equal to 0. These are going to be equal to the negative of the, well, let me move this negative later to the other term, the compliance matrix, something that we have seen already, and here I'm assuming an isotropic solid. So this is the compliance matrix. By the way, you could extend also this to an anisotropic solid. All right, I have my compliance matrix, and this is multiplied by this tensor, which in vector form and bringing the negative sign is going to be 3 beta k theta. And it is the same in all directions. And what I get from here is that the deformation in each direction is going to be the same because this is an isotropic solid. For example, epsilon 1, 1 out of these equations, I will have to do the first row times the column, and this is going to be equal, as you can see, this is going to be a common factor, so I need to add all of this, and this is 1 minus 2 Poisson ratio. This 2 Poisson ratio comes from over here. All of that times the 3 beta k theta. Okay, but I'm going to take advantage of something over here. You may go ahead and check your notes, and you will see, let me get this negative sign over here. You will see that what I have here is actually 1 over the bulk modulus. So this equation, let's see, over here, this is actually 1 over k, where k is the bulk modulus, and this is the quality of the isotropic solid. And since I have a k here and I have a k there, actually all of this is going to cancel out, that k with this k. And therefore, the strain in direction 1 is going to be negative, the 3 disappears, is going to be negative beta theta, or the change of temperature. So, for example, if, let me frame this result because it is very important. If delta theta, which is equal to delta t, it's larger than 0, that means that I have an increase of temperature, then this would produce a negative change of strain, or according to the geomechanics convention, then this is going to be, let me rephrase, I'm not sure if I said correctly this before. If I have a positive change of temperature, that means an increase in temperature, then, okay, this is going to be positive, and all this result is going to be negative. And a negative change of strain, according to the geomechanics convention, that's going to be a dilation. On the other hand, if I have a change of temperature which is less than 0, and that means that the final temperature is smaller than the initial temperature, then that means that I'm going to have negative and negative, that's going to become positive, and the change of strain is going to be positive, and according to the geomechanics convention, this is going to be a contraction of the solid. So you may ask yourself, what are typical coefficients of linear thermal dilation? And I can tell you that typically for rocks, beta is in the order of 10 to the minus 6 to 10 to the minus 5, 1 over Kelvin. And for example, if you were to have a change of temperature of more or less 100 degrees C, which is the same as a K in terms of the change, there is just an offset in the origin, what is 0, then 100 times that will tell you that the expected strains will be in the order of this one times 100, 10 to the minus 4 to 10 to the minus 3. And this is what you see over here. Let me clarify here. I mean 2. And these strains, are not that negligible. They look very small. And probably for soft sediments in which you have strains in the order of the percents, this is quite small. But for rocks, it is not. And therefore, we're going to see that such thermal strains could be quite important in applications of rock mechanics. Okay. We see also very clearly in this equation that the thermal dilation coefficient or linear thermal dilation, it's exactly the proportionality parameter between a change of linear strain and a change of temperature. And this is actually the definition of the linear thermal dilation coefficient. And it refers to strain in just one dimension. That's also why we have a number 3 over here. Don't be confused, because many times people use another thermal dilation coefficient, which is 3 beta altogether. So be careful about that. Here we are developing our equations using the linear thermal dilation coefficient that comes from this equation. So just by proceeding backwards, then we have shown that applying this definition results in this type of strain, a linear strain proportional to temperature and proportional to this coefficient. Okay, let's go ahead now and do the next type of test, which is called constrained dilation. In a constrained dilation case, what we're going to do is we are going to change the temperature, similar to what we did in the previous example, but we are going to, in this case, change the boundary conditions. So now the solid is going to be subjected to no displacement boundary conditions. In this example, in all directions. These schematics, these triangles, are meant to represent rollers. And I'm going to increase the temperature here. What do you think is going to happen? If I don't let the solid expand, what would happen? Well, the answer is that if you increase the temperature and this solid tries to dilate, but it can't, as a result, it's going to develop a thermal stress. And basically, here at the boundaries, now we'll have a buildup of stress, like for example here, that is going to be a compression. And our objective is going to be to calculate how much that compression is going to be. So let's use again the constitutive equation that we proposed before, and we're going to calculate that stress. All right, in this case, the strains are going to be 0. So I'm going to get rid of that term. And actually, the solution is going to be quite simple, because I already have the stress over here, and this is going to be the answer. Again, in this process, I'm going to ignore the shear stresses, because if this is isotropic, I'm not going to generate any shear stress. I'm just going to have normal stresses, and in this case, these are going to be sigma 11, sigma 22, and sigma 33, and all of those are going to be the same for an isotropic solid and are going to be equal to 3 beta k delta t, or theta, as we called it before. It's the same thing. Okay, so for example, if we have a change of temperature which is larger than 0, and then that means this one is larger than 0, beta and k are just material parameters and they are positive, so all of this is going to be positive, and the stress also is going to be positive. And that means that your change of stress will also be positive, or you will have more compression according to the geomechanics convention for science. And let's just pick one of these answers. For example, sigma 11. And also you may wonder, what are the typical stresses that I would see with a change of temperature? Well, let's go ahead and let's imagine, in this case, typical rock parameters with beta equal to 10 to the minus 5, 1 over Kelvin. Let me add a degree actually here to not to confuse this Kelvin with a bulk modulus, and let me add the same over here. Okay, this is a degree Kelvin. And let's say that the change of temperature, theta, this is going to be a large change of temperature, or 100 degrees Kelvin. And what else do I have here? The bulk modulus. And the bulk modulus K is equal to a rock with 10 gigapascals. Well, we can put all of these together, and you are going to get that sigma 11 then is going to be equal to, as we see over there, 3 times 10 to the minus 5, 1 over a degree Kelvin, times the bulk modulus, which is 10 to the 10 pascals, and this times the change of temperature, which is 10 to the 2 degree Kelvin, or degree C, is the same thing. And after we can get rid of the Kelvin, and you see we just have pascals over here, and this is going to be equal to, in this case, 10 plus 2, 12, minus 5, that's going to be 7. So this is going to be 3 to 10 to the 7 pascals, which is equal to 30 megapascals. And if you multiply this by 145, more or less, you're going to get that this is more or less equal to 4,400 psi. And this is a relatively large stress. And notice that it's in the order of the megapascals or in the order of the 1000 psi's. And let me just add, in this case, this is a compression. If you have the opposite, if you have a drop of temperature, then instead of a compression, you have a tension of several megapascals. And the tensile strength of rocks is just a few megapascal for most cases. A very strong rock has a tensile strength of about 10 megapascals. So with such a shock of temperature, we see that the equations tell us that we can create significantly large tension or compression stresses that are going to affect the equilibrium of the rock, and sometimes they may also lead to failure.